The example goes like this. There is a solution, handwritten solution. There is a video solution from last year. There will be another one from this year, so you can't really miss it. It's just, you can't miss it. No way you can do that. If you miss that, it's certainly not my fault. Right, so the example says this. We given three vectors, A, B, and C, and we assume that they are linearly independent. And now, basing on that, we build another four vectors, P, Q, R, and S. And that's exactly how we build them via these identities. Like this, like this, like this, or like this. The question goes to show that goes to ask to prove that these new four vectors will be in fact linear dependent as opposed to original three vectors being linear independent. It's a relatively simple question, especially for the person who spends some time with this, but for you it's like a good demonstration how sometimes things work in this area. Right, so all we have to do, we have to pick up the definition of linear dependence. I just showed it to you before, and I just try to quote it now. So the definition says like this. So we have to look into linear combination of these four vectors. We have to look into linear combination. Here it is. Yes, and we have to ask whether we will be able to find, one way or another, doesn't matter which way, but whether we will be able to find some choice or some choices for these coefficients, and I use the letters x, y, z, and w for those letters, x, y, z, and w, whether we will be able to find these numbers, these are the numbers, real numbers, whether we will be able to find such numbers such that not everyone among them is zero. Of course, we can choose a zero choice. It's a trivial elementary choice. If I choose x0, y0, z0, w0, obviously this identity will be true, but it's a trivial side of it. We're looking for the non-trivial side of it. If we can find the non-trivial side of it, then we're done. Any non-trivial side. So any non-trivial choice for these four coefficients will do. Will let us to conclude that the system is linear dependent. Now let's just see how I can choose those coefficients. Well, obviously my first step will be just subbing in the expression for P, Q, R, and S in here in terms of A, B, and C. That's the first step. Seems to be a very natural step, in fact. If I do that step, here it is. Here's my substitution. X times A plus B, that's a sub-in for P. Then goes P take C, that's a sub-in for Q. Then goes A take B plus C, that's a sub-in for R. And then goes W with the vector. If I sub in the expression for S, it will be B plus 1/2 of C. That's nothing serious here happened. We just did a regular substitution of one thing for the other things. Now the next step which I will suggest will be rearranging the terms in this expression. I want to rearrange the terms in a way that all A vectors in one place, all B vectors in one place, all C vectors in one place. It's again quite natural kind of step. If I rearrange them, the A will come with the coefficient x from here. Let's just see what I have. So if I rearrange this, x will come with the coefficient x from here, z from here, and that's it. That's all presence of A in my expression. There's no more A left. Next comes B. B comes with the coefficient x in here, y in here, here it is, and negative z from here, here it is. Actually, sorry, B also comes with the coefficient w. That's a fourth term in the bracket next to the vector B. The final rearrangement will be all about vector C, and that's the rearrangement. Negative y, it is from here. Z, it is from here, plus z, and w on 2, it is from this one and this 1/2. That's all possible coefficients we have next to vector C. That's my rearrangement. That's again sort of like elementary algebraic manipulations. Now comes the real new piece, basing on our definition of linear independence. Remember, we started with the assumption that A, B, and C linear independent. And we're looking down here at the linear combination of these three vectors, A, B, and C. It's just this time the coefficients we have, they're no longer just single symbols, single letters. This time they are sort of longer expressions, but still they are numbers, and still our definition for linear independence, it is still true. So I can conclude, now I can conclude, that every bracket here, this bracket, and this bracket should be 0, because my A, B, and C linear independent. Here's my conclusion. I'm going to put this in writing now. Here's the bracket number 1. Here's the bracket number 2. Here's the bracket number 3. And I'm going to look at these 3 identities as a system of linear equations. Right, let me now summarize what we achieved so far. Remember, we started with the identity like this. Remember, our grand objective, finding 4 numbers, x, y, z, and w, not everyone is 0, such that they make this identity true. That's all we need. The rest is irrelevant. Okay, and on the course towards this objective, we come up with the 3 identities like this. So we come up with the conclusion that if we need these 4 numbers, no matter what, these 4 numbers will be subject to these 3 identities. So if I need these 4 numbers to make this vector identity true, I need 4 numbers at least which will make these things true. Well, I say at least. In fact, at least is not supposed to be in this sentence. Because if these 4, sorry, I said 4, I mean 3. If this 3 identity is true, of course, then this vector identity is true, then this vector identity is true, and then this vector identity is also true. So in fact, it is if and only if statement. In our objective to find x, y, z, and w such that this happens, we can replace this objective now with the objective finding x, y, z, and w such that these 3 numerical identities happen. And again, we still have this extra requirement that our choice, whatever we find, not every number we find should be 0. Again, the trivial choice 0, 0, 0, 0 will do. If I put x 0, z 0, y 0, w 0 across these identities, that will be true identities. But it's a trivial choice. This is a trivial choice we're not interested in. Basically, this is all on the conceptual side of this example. The rest is just a computation, the way to find these 4 numbers. I'm sure you came here with a sufficient background in system of linear equations. And I know, well, sufficient background, and I suspect that you all have your own ways of doing this kind of task. I'll show you my way right now. It's sort of like ad hoc solution. Later on, if you check the lecture notes which I published, later on you'll see that actually we're going to study the systems of linear equations and the way to solve them in a very systematic way. You will be bored to death by the time we finish with that systematic way, with the way we solve system of linear equations. So right now I just do that sort of like ad hoc solution. I don't want to bother you too much with this. Trust me, you will be bothered very much with the system of linear equations in 5 weeks' time. Well, now the main thing which is interesting here, I think, is just we need to find a solution which is not zero, not trivially 0. And I'm going to just make this straight away. I'm going to just say I'm going to find a solution where w equal 2. Why not? It's a bold choice. It's a bold call, actually, right? I might fail on my course, and then it's just a wrong choice for the w, but I think I will succeed. My intuition tells me that I will succeed. It will be part actually of that training, of that systematic training in system of linear equations, to train your intuition so you can make this kind of bold calls also with a high rate of success. Okay? So far, it's only me who has this high rate of success, so I hope you will trust me. W equal 2 will do. Let's just see if it's so. So I'll just take w equal 2. I will solve here for x probably. Let's just solve for x from the first equation. Easy solution. And now what I'm going to do, I'm going to put these numbers into the other 2. So I take this, I will sub these 2 into this. Wrong key sequence. Again, I choose this 2, and then I substitute here x and w. Yeah, we can, of course, this is a direct substitution. I can simplify this a little bit. Yeah, I can do the same thing here. I can take this equation, I can sub in W, I can sub in X. Here's my substitution. Oh, well, it doesn't do the arithmetic straight away, but we can ask politely for that. And we come down to the system like this. I think even your intuition at this stage, can tell that this system will be solvable. This system will be solvable. And again, there are a number of ways you may have how to solve this system. I'm not going to bother you with that. I'll just bluntly use the software straight away and just do like this. I choose these two. I'm sure it will suggest me to solve for z and y. Again, if I choose these two, if I ask for the solution, now I have them. Here they are, z equal 3 and y equal 4. Here's my solutions. Here's my bracket. Well, of course, I have to say x also. If I sub in z for x, it will be -3. I claim that the values x equal -3, y equal 4, z equal 3, and w equal 2, they will make all three of these true, and by implication, they will make this one true. And that concludes my